Okay, what we're going to look at is a situation we've had before of an inclined plane. All right, and we have an object on the inclined plane. Let's say it's mass m. And we're interested in how fast it's going when it gets to the bottom, after it's slid a certain distance down the incline. So that implies that the incline is inclined enough to allow that to slide down. So the force pushing it down from gravity has to be enough to overcome friction. So there is a force of friction going on here, and there is a coefficient of kinetic friction that would be given in the problem. All right? Now, of course, from our previous work, we know that there is a force of gravity on the object, mg. All right? And that force of gravity is, you can break it down into a force parallel to the surface of the incline. Okay? And so that's that vector right there, that force. And then perpendicular to the surface would be another vector right here, which would be the same magnitude as the normal vector. And of course, what we have here is a right angle. All right, and if you look at this as being theta, the angle of the incline, and you know we have two parallel lines here, so these angles are the same. These two angles are the same, so theta must be over here. Okay, and then as we've said before, this force parallel to the incline, which will denote force parallel, is related to the sine function. All right, that side is opposite. Okay, so we see that force parallel, this side here, would be mg sine theta. That would be that force right here, which we call force parallel. And then there's a force pressing onto the surface, perpendicular to the surface from this mass, and we'll call that force perpendicular. Okay, and that of course is equal to mg cosine theta, because relative to theta, this side here of the right triangle is the adjacent side. And then as it slides down, it's the force parallel, if it's large enough to overcome gravity, and it's large enough then to accelerate it down there, we can get it moving down the incline. Okay, so what will that mean? Well, the force net will be equal to this force parallel, okay, minus the force of friction. And the force of friction, of course, is the normal force, this force we have here, multiplied by the coefficient of friction. So we have UK mg cosine theta is the force of friction. The net force then is the force downward, the parallel force, minus the force of friction. So that's going to be mg sine theta minus UK mg cosine theta all right. And what's that going to give us? Well, we can factor out the mg, and the net force is equal to mg sine of theta minus UK cosine of theta. Okay? That's a net force on it. Now, if we figure out the distance it goes, and that force is going to be applied over a distance, there'll be work done by this net force. So the work is going to be equal to the net force times the distance. Okay, it's going to slide down there. That'll be the work that goes into it. Now that work, some of it is wasted by overcoming friction, and some of it goes into accelerating the object. So, you know, the net force takes care of that. The net force is subtracting out the force that goes into friction, and so it's just the force that's going to be accelerating it down the incline. So that work, as it goes down the incline, is going to speed up. So that work, that net force work, will go into increasing the kinetic energy. So F net times D, which is that work, will be changed into kinetic energy by the bottom, okay, which will be 1/2 mv squared. So that work energy is going into accelerating the object, and the object then gets a greater velocity. And so in the end, this energy, this work that was done by gravity and sliding it down the incline goes into kinetic energy of the object. All right, so now if we go back and we replace some stuff up here, we'll see that F net mg sine theta minus uk cosine theta. All right, that's then times d, the distance it slides, okay, will equal the kinetic energy. Okay, so the kinetic energy is 1/2 mv squared. And the first thing you notice is that m cancels out. Doesn't matter. And we had a lab earlier in the year, if you recall, we had an inclined plane, and we took different masses down the inclined plane, and we used the sonic ranger to figure out how fast it was going, or what its acceleration was. And we found out that it didn't matter what the mass was. It always had the same acceleration down the incline. And here, mathematically, we see the same thing going on here, is we see that the mass disappears. So we have this interesting relationship for figuring out the velocity. That 2 can come to the other side. So it's 2g, and then we have sine of theta minus uk cosine theta. And I think I'll put the d here over out in front. So let me just erase this and put 2gd sine theta minus uk cosine theta equals v squared. So if you need to find v, obviously you take the square root of this quantity, okay, because this is v squared. Now next, what if we want to find out how much time it takes for it to go down the incline before we found out how fast it would be going? Oh, there's different ways to do this, but let's take a look at this relationship here, and let's utilize this relationship to figure out what the time is going to be to go down the incline. Okay, so what we know is that this force net from the previous work that we did, the force net is equal to the parallel force down the incline minus the force of friction. Okay, so we derived that last time as being mg sine theta minus uk cosine theta times t would be the mass times the velocity. Okay. Now, the velocity that we had a formula that we were able to figure out before, all right? And that formula, from over here, solving that formula for v would give us square root of 2gd sine theta minus uk cosine theta. Okay. We left it in the first part as v squared. Well, I'll show it to you here. You can see what we did in the first part, right? We left it as v squared is equal to 2gd parentheses sine theta minus uk cosine theta close parentheses. But I'm solving for v there, so I can plug it into this formula. And you can see it up on the screen now that, this is the relationship for v. And again, when we look at this, we see that m disappears. It's not really relevant in how long it takes the object to go down the inclined plane, as we said before. So let's just solve this for t. T equals the square root of 2gd sine theta minus uk cosine theta divided by, well, this quantity here, which is g, and then we'll have sine theta minus uk cosine theta. Now we can do a little bit better with this in terms of simplification. And g is really the square root of g times the square root of g. And this quantity is the square root of this quantity times the square root of this quantity. So I guess what I'm saying is we could simplify t, and we can break this apart. There's the square root of 2, square root of g, square root of d, square root of sine theta minus uk cosine theta. And then the bottom of this fraction, I'm going to take this g and make it square root of g times square root of g. Okay? And then this will be the square root of sine theta minus uk cosine theta times its square root. Sine theta minus uk cosine theta. And that was done in order to do some canceling. Okay, so you see that this and this will cancel. And this square root up on top will cancel, right? And you'll get one of the square roots down at the bottom. Okay, and then if you look carefully, square root, square root, square root, square root. So we can pull the square root out of the whole thing, and we can get t is equal to one big square root. And on the top we have 2d parentheses sine theta minus uk cosine theta. And then underneath, this is still part of the same big radical. We have square root of g. We have g, actually, because we got the square root of the whole thing. So there's g, and then I think I made a mistake here. The top doesn't have that. All right. Top is just 2 and d, and we cancel that out. So it's the bottom, which is g, and then times sine of theta minus uk cosine theta. Okay? So that's a big square root over the whole thing, and that's a fraction inside. All right? So 2d, and the g on the bottom, and then the square root is in the denominator. That should do it. That would be the time it takes to go down the incline. So there's a time it takes to go down the incline based upon how far it went down the incline, and g in the angle, and of course the coefficient of kinetic friction. And we also have the other relationship that we had earlier, which is the one where we can find out how fast it's going by v squared is equal to 2gd sine theta minus uk cosine theta. So all this was obtained, how fast it's going down the incline, as well as how long it takes to go down the incline. All this was obtained not by using the kinematic equations that we used earlier in the year to do a problem of something like this, but by using, starting out with energy and work, okay, and then we did use the idea here from momentum. Okay, so we have a momentum formula combined with an energy work formula, which can solve a problem that we did earlier in the year with kinematics. And I think these two equations are kind of neat, and we'll have some problems on those in the not too distant future.